We stopped here last time. This one discussed before. We said that this is a merchant circle, as you can see here, and this is a tool, and this is a cutting. And we said that when cutting happens, shear stress actually increase up to the maximum. When you get the maximum shear stress, I mean chip will start separating here, right? That's what we discussed last time. And then we put the shear stress equation. This is the shear stress equation. And we differentiate the shear stress equation equal to zero to get the maximum. To get the maximum shear stress, we differentiate. This is shear stress. This is the shear force equation as we described earlier. And this is a shear stress equation, which is equal to Fs divided by As. And this equation, as we described last time, is a shear stress equation. To reach maximum shear stress, we differentiate this one with respect to the phi, or the shear plane angle, and make it equal 0. And when we make it equal 0, we get this equation: phi equal to 45 plus alpha divided by 2 minus beta divided by 2. And we said this equation is valid when you do cutting. This equation is valid when you do cutting. Whenever you have a chip separation here, shearing, and a chip separation here, this equation is valid. And this equation actually is important too, because she can be used, or this equation can be used to obtain the relationship between phi, alpha, and beta, right? And also, we last time we solved this problem. We solved this problem last time. We stop here what merchant circle equation tell us, and base this on this equation. As the rake angle increase, the merchant circle tell us that when rake angle, where is the rake angle? This is the rake angle, right? This is the rake angle. Rake angle is this angle. This is alpha. This is the rake angle, right? So rake angle increase. Let me just say, rake angle increase in this direction. Whenever like this rake angle increase. Whenever like this rake angle is decrease. Rake angle decrease in this direction, rake angle increase in this direction. So this one is positive. Rake angle is positive. This direction, rake angle is negative. Right, so rake angle here increase. This is a positive direction. Rake angle here increase. Rake angle this direction decrease. So when rake angle increase, when alpha increase, mean alpha is higher, phi is get bigger. You get bigger phi also. You see that whenever alpha in the equation, whenever alpha increase, phi also increase, right? Whenever, just regardless beta, whenever alpha, which is a rake angle, whenever the rake angle increase, phi also increase. Phi is a shear plane angle, right? And vice versa mean whenever the rake angle decrease, as you can see here, this is a smaller rake angle. So rake angle here is 0. Rake angle here is positive increase. Whenever rake angle decrease, phi also decrease. Get a smaller alpha, smaller phi, bigger alpha, bigger phi. So smaller alpha means smaller phi. You can see that what happened. Bigger phi, smaller phi, what happened? Whenever you have bigger phi, you get small, this one, I mean, this is we call is a shear plane. Shear plane is shear plane length. Shear plane length is smaller, you get smaller chip thickness, smaller chip thickness. As you can see, whenever phi is smaller, whenever phi is getting smaller, you get bigger chip thickness length. What is the difference between smaller and bigger chip thicknesses? Whenever you have bigger chip thicknesses, you can see that a chip thickness is increasing, and this is need power, high power, because the tool now removing a bigger amount of material. Here, tool removing a smaller amount of material. So this one is desired. And whenever alpha increase, phi increase, chip thickness or cut chip thickness will getting smaller, and power here needed to the cut will be less. force and power will be less. This one is a good case, but whenever alpha decrease, phi also smaller, you get lower alpha, lower phi, and then what happened? Shear plane length will increase and chip thickness increase, material removal tool will big remove, I mean, push big amount of chips in, meaning the power and force will also increase. Right. Uh, this increase also shear angle, reduce the chip thickness and reduce the temperature rise. Temperature also. Here temperature is less, here temperature is higher. That mean here high power, let me just conclude. In this case, high power and also high temperature. This one associated with high power and high mean when alpha is smaller, you get phi is smaller, you get high power and high. Any question? High power and high temperature. When alpha is bigger, phi also is bigger, you get less power and less temperature. This one reducing is desired. Someone will say that okay, make alpha bigger. Yes, this is the tool angle. Alpha is the tool angle. If you would like to change alpha, you have to find another tool because we are not manufacturing tool. We're buying tool from the market. So when we buy the tool, you have to buy a tool with a smaller, I mean, with small alpha. Then also this one is not good to make it alpha the smaller and smaller or increase alpha. If you increase alpha means that the tool angle, this is the tool angle will also getting smaller and tool become weak. So also there are a limit. You cannot just increase up to, you have there are recommendations, then we cannot increase forever. Then you have to also consider that alpha should be increased within certain limit based on the recommendation to keep tool strong enough to do the cutting process. Any question? Okay, then the shear plane angle can increase shear plane angle. Then the question is, which is better, to increase the shear plane angle or make a small to increase shear plane angle? Higher, higher shear plane angle is better. To increase the shear plane angle, what to do to increase shear plane angle? Actually, two things: increase alpha and decrease beta, smaller beta also. Then beta, smaller beta, to increase phi, you can do either by smaller beta or higher alpha. In this case, you get phi bigger phi. Then let me say alpha bigger alpha, you get bigger phi, smaller beta also, you get bigger phi. So to increase phi, to increase the shear plane angle, either you can increase alpha or reduce or getting smaller beta. This both cases you increase phi, which is desired as we described. So temperature will be reduced, power and force will be reduced, and this one desired. Alpha is to buy new tool. How to increase alpha? To increase alpha, you buy a new tool, you get a new tool from the market with bigger alpha, but beta, to reduce beta. What is the beta? Beta is the friction angle. Beta is a friction angle. To reduce beta, to make it beta smaller, this could be done by reducing the friction. You must reduce the friction because beta is a friction angle. Beta, tan beta equal to F divided by, equal to mu, equal to F divided by N. So to use beta, then friction force must be reduced. To reduce the friction force here in a cutting zone, you can lubricate. So reducing angle, this one increase the proper tool design, and the friction angle can be reduced by using lubrication. Lubrication in cutting. We do lubrication in cutting. Use lubricant cutting fluid or use lubrication in a cutting. You lubricate here, reduce the friction. Then when you reduce the friction, beta will be reduced and then you can increase phi. Any question? Okay, next, power and energy relationship. Power and energy relationship. In a cutting, power is very important. We have to be concerned about the power. Power usually is generally power equal to FV. Generally power to equal all only is I mean sorry is power always I mean generally power equal to FV. F is the force, V is the velocity, FV is the power, right? And we have six components of the forces: one, two, three, four, five, six. Shear and normal. This is the cutting and thrust, and this is the friction and normal to the friction. We have six components of the cutting force. So this is the power equal to Fv. However, we have only three components of the velocity. This is one component is the cutting, another component is the chip velocity, another component is the shear velocity. So power equal to Fv. Must be Fv, I mean force multiplied by velocity. Two vector must be in same direction, must be in same direction. Then you can see that, we can say that we have the cutting force and cutting velocity in same direction. We have shear force and shear velocity in same direction, and we have friction force and chip velocity in same direction. Only three components of the force will be considered here. These three components of force that we're going to consider in the same direction of the velocity vector, because we have only three velocity vector. Then for calculating the power, only three forces will be considered, which is the cutting force, shear force, and friction force. Fn and F thrust and the normal force will not be considered because there are no velocity in this force direction. Then when you come to the power, you can see that the B cutting, as I told you, this is a B cutting. This is a B cutting here. We have force in the cutting and we have velocity in same direction. Can you see that? Can you see that? This is the velocity, this is the velocity, and force in a cutting direction. So BC equal to FCV. This one FC cutting force multiplied by V. Okay, FCV is the one power. So the power in a cutting equal to FCV. Another power is equal to FSVS. This is the VS. This is the VS. This is the V, horizontal. Horizontal is the V. VS is the chip velocity in the same direction of the shear velocity. Shear velocity exactly in same direction with the shear force, and chip velocity in same direction with the friction force. Can you see that? Yes, two. Then three component of the power. First one is power. We call it is the BC equal to BS plus BF. BC is the power in a cutting equal to FCV, FC multiplied by V. Another one BS is power in shear equal to FS multiplied VS, and power friction equal to F multiplied by VC. What is that? This is the main power. This is the main power delivered. FCV is the main power here delivered by the tool to do the cutting. And then there are another two, but this one equivalent to the two other powers. This power that delivered by the tool require to shear the material and overcome the friction in the cutting zone. Right. To this power delivered by the tool, this is a power delivered by the tool, should equivalent to the power needed to shearing the material and power needed to overcome the friction in the cutting zone. Then the power delivered by the tool equal to FCV equal to the power needed to shear the workpiece or shear the material, which is the FSVS. This is the power needed to shear the material in the shear zone, plus the power needed to overcome the friction in the cutting. So this one should equivalent, at least should equal to this one or bigger than this power needed in the cutting process. So BC equal to FCV plus FCV, this is the power equal to FSVS plus F multiplied by VC, sorry. Any question? This is the power, three component. Main power delivered by the tool, power to shearing the material, power to overcome the friction in the cutting cutting zone. We have whatever we call is the unit power. Whatever we call is a power. We have whatever we call is the unit power. What is the unit power? Unit power or specific energy, same meaning. Unit power or specific energy, same meaning. Unit power actually, let me, please listen to me carefully. Unit power is the power divided by material removal rate. Material removal rate. Power divided by material removal rate. Then you get what second per cube material removal rate, which is a cubic millimeter per second. Then if you divide what is a power, if you divide power, which is a watt, by material removal rate, which is a cubic millimeter per second, you get what second divided by cubic millimeter, or what is a joule per second, then you get joule per second multiplied by second, then you get joule per cubic millimeter, or you get newton meter per second. You get newton meter per second. It's same also. All these units are same, either watt second per cubic millimeter, or joule per cubic millimeter, or newton second per newton meter per second. All same meaning. Then it is the power divided by material removal rate. When you do like this, you get a unit power. Unit power mean power per unit material removal rate, or volume of material removal per cubic millimeter per second, per 1 cubic. So this is a power required to cut 1 cubic millimeter per second. This is a power required to cut 1 cubic millimeter material removal rate, 1 cubic millimeter per second. What is the benefit? There are a big benefits to do this. There are a big benefits to do this. What is the benefit? The benefit is that I can measure it. For aluminium, I can measure the power needed to cut 1 cubic millimeter per second. For copper, for steel, and so on. Because it is cut only 1 cubic millimeter per second, then I can measure it. I can measure it for all material and put in the table. Put in the table, then you can have it here in the table. This is the power. This is the unit power or a specific energy. This is the unit power or specific energy for different material. We can measure it. We can put in the table. Then we put in the table. So when we put in the table, actually, later, if you need to know what is the power to cut carbon steel, then you can obtain from the table. You multiply by the material removal rate, you get the power needed to cut this material. Then this is a benefit to put in that table, right? Then again, unit power is the power divided by material removal rate. Material removal rate is the VTOW, VTOW or VFD. This is a material removal rate. Material removal rate is equal to VFD or VTOW, same meaning. Because TO equal to F. TO here, we discussed TO is the uncut chip thickness, or equal to millimeter per revolution. Millimeter per revolution means that tool will cut TO and another TO and another TO. Then TO here equal to F, which is millimeter per revolution. And W here is the width of cut or depth of cut. Width of cut or depth of cut. Then VTOW, this is the material removal rate. Then the power equal to F, for example, the power equal to the main power equal to FC multiplied by V divided by VTO. W, then V, go with the V. As you can see here, V here, same V. We have here same V. This is the same V, then V go with the V, then equal to FC divided by TOW. In this case, this is a unit power in cutting, right? And FC unit cutter, this is the cutting force, this is the main cutting force, or this is the cutting force, TO and W. This is the unit power, right? So as I told you, unit power is put in the table. However, this table indicating that this is the unit power up to TO equal to 0.25 millimeter. This is the unit power calculated up to TO, the uncut chip thickness, equal to 0.25 millimeter. It is in the table. Actually, we can get from the table and we can use it to calculate the required power. Unit power also equal unit power of friction and unit power of shear. Same, from the same equation, unit power of cutting equal to unit power of friction plus unit power of shear. This is the unit power of cutting equal to Fc divided by WTO. Unit power of friction equal to FVC divided by WTOV. Here not equal, not same. Here in this case, in the first case, in the cutting V equal to V. V equal to V, then FC WTO, but here we not same. Then here FC, this is the F, this is the friction force multiplied by V shear. This is the V, sorry, V chip divided by WTO V cutting speed. Those are different. And here Vs unit power in shear equal to Fs Vs shear force multiplied by shear velocity divided by WTO V here is the cutting velocity. This is the unit power, right? Next is size effect. The size effect, actually, this unit power in the table, this unit power in the table that we listed in the table or we show in the table, affected by the wear, affected by the wear of the tool, and affected by the TO if TO bigger than 0.5, because this value in the table calculated as a sharp cutting tool meaning no wear. It is totally new. We use a new tool to cut and calculate the specific power, and chip thickness is before cut, which is a TO equal to up to 0.25, up to 0.25, bigger than 0.25. We shall consider some other approximation. In the first case, for worn tool, if we're not using a tool, if you have a worn tool, then we have to multiply the factor, because the power will increase whenever the tool getting wear. The power will increase, then we can measure the wear, or we can calculate the wear in somehow, and we can multiply this one with certain factors. The unit power obtained from the table can be calculated or multiplied certain factor to compensate the effect of the wear, like for example 1, like the example 1.25, 1.3, and so on, based on the wear in the tool. Next, the effect of the TO. If the TO bigger than 0.25, if TO bigger than 0.25, what we can do? Actually, they said that this figure can show if the TO bigger, for example, TO here, this is the TO. This is the TO uncut chip thickness. This is the TO. If TO bigger than 0.25, for example, if TO equal to 0.63, then you can, this is a correction factor. Correction factor can be obtained as 0.8. For example, then you multiply 0.8, then you get the unit power. You get the unit power. Whenever you get the unit power, whenever you get the unit power, you get the unit power from the table, you get the unit power from the table, and you multiply the correction factor, then you get the correct value. Or correction factor, this correction factor either can be used this one or calculated by KCFTO power minus 0.21, which is a KCF equal to 0.75. This one is the constant equal to 0.75. TO, you can obtain both TO here, which is a bigger than 0.25, then you can obtain the CF correction factor, then you multiply correction factor to get the value. Okay, let's take an example. Let's take an example. Please give me your attention here. A turning operation is carried out on aluminium. Okay, this is a turning operation carried out based on the specific energy value in table 17.2. That this is the unit power or a specific energy we can obtain from the table. Determine the material, what is the material removal rate and the cutting power in the operation under the following condition. First case, this is the A and B. This is a two question here. This is A. This is the first case. This is B. This is the second case. So what we need? We need we need to obtain the material removal rate and the cutting power. What is the material removal rate and cutting power? First case, cutting speed 5.6, feed 0.25, and depth of cut is equal to 3. Right, this is the first case. Second case, cutting speed equal to 2, feed equal to 0.6, depth of cut equal to 5. Here you can realize that feed actually here, to remind you the feed here, which is millimeter per revolution, is the TO. This is the TO. This is the feed, right? This is a millimeter because the tool here we cut TO and another TO and TO. So TO every one revolution. Then feed. This is the one. This is the one here. So this is the one here. This is the one here. Right. This is the feed. In two cases here, you can see that this is the TO. So now we talk about the TO. This is exactly TO. Depth of cut is the width of cut. So to remind you, this is the TO feed, which is the TO. The feed here is the TO. Depth of cut is the width of cut. So it is same. Depth of cut is 3, depth of cut 5 mean. This is the depth of cut. This is the depth of cut here, which is equal also width of cut. In the first case is 0.25, then no issue. We can just obtain directly the specific energy from the table. In the second case, it is equal to the TO equal to zero point 0.6. 0 0.6, can you realize here 0.6 is bigger than 0.25. In case TO bigger than 0.25, you must use a correction. You have to use a correction factor. You cannot just simply get the specific energy from the table and use it. Okay, from the table 17.2 for cutting aluminium, specific energy equal to zero point 0.7. This is a specific energy. Then from the table, the specific energy equal to zero point 0.7 for cutting aluminium. Okay, we're going to use this one. Right, so we have speed and feed and depth of cut. Then material removal rate equal to VFD. Then VFD, speed equal to 5.6, F equal to 0.25, and D equal to 3. Then you can obtain it. No issues. This is the material removal rate. Power, the cutting power equal to material removal rate multiplied by U material removal rate. Yes, because this is the unit power equal to power divided by material removal rate. Then power equal to specific energy or unit power multiplied by material removal rate. Unit power equal to 0.7. Then 0.7 multiplied by the material removal rate. So here, no issue. Here, no issue, then you can obtain the power. Why no issue? Because it is up to 0.25, no problem. So we can simply obtain directly. We can obtain, as you can see here, you can obtain the unit power from the table, and directly you can use here without any change, because this one up to 0.25 is okay. Right. Second case, if the unit is TO equal to 0.6. Second case, if TO equal to 0.6. This is the second case, right, which is B. What are you going to do with that? In this case, if the feed is 0.6, in this case, we must calculate the correction factor. Correction factor equal to KCF, which is constant, which is equal to 0.75 multiplied by TO power, so on. But TO equal to 0.6. Feed here is the TO equal to 0.6. Then 0.75 multiplied by 0.6 power minus 0.21. Then you get, this is the correction factor. We have to consider the correction factor. Okay, material removal rate is no issue. VFD. Then VFD, this is the V is equal to 2, F is equal to 0.6, D equal to 5. VFD is okay, material removal rate. When you calculate the power, this is for aluminium. For aluminium here, this is 0.7. This is, you obtain this one from the table. I mean, unit power from the table is equal to 0.7. Not enough. Then you have to multiply 0.7, as you can see here, because is TO bigger than 0.25, then you have to multiply by correction factor. Then you have to multiply by the correction factor. Can you see that? Then you have to multiply unit power. This is the unit power. Unit power here equal to 0.7. You must multiply by correction factor. You must multiply by correction factor. Why we do that? Because the TO bigger than 0.25. Because the values in the table up to 0.25. More than 0.25, you must multiply correction factor. Then, okay, material removal rate multiplied by U. Then you can obtain the power needed in this equation. Any question? Right, next is example. Let's see the example together. Continue with the previous example. Let us determine the power and the specific energy. We need to obtain the cutting power and the specific energy U. We need to obtain the cutting power and specific energy in the machining operation for cutting speed. 100, summarizing TO and W and F is given here. We have FC, cutting force, W, width of cut, TO is equal to 0.5, and the cutting speed equal to 100. Then cutting speed we know. This is a cutting speed, right? This is a cutting speed. This is the FC. FCV is a power. Then he need a power. Power equal to FCV. Then FC multiplied by V. Alhamdulillah. FC multiplied by V, this is the power. Then you can obtain directly the power. Power is here, right? So first the question, what is the power? Give me the cutting speed, and give me FC. FCV, then FCV multiply FCV, you get the power. This is the power. Second is Ahmed, just give me a second. FCV here, you multiply by FC multiply by V, then you get the power. This is the power. And we need the unit power. Unit power equal to what? Unit power equal to power divided by material mover rate. Material mover rate equal to VFD or VTO. V is here, TO and W is here. This is the TO, this is the W, or VFD. Then you multiply VTO W. This is all value is given. Then you obtain. Here someone will ask me. TO is bigger than 0.25. TO is bigger than 0.25. Shall we calculate the correction factor? And we consider here to calculate U? No, we don't have to do this. Why? What is the difference? Why we don't do this? Because this U is calculated actually. This is the actual U. This is the actual U. This is the actual unit power calculated based on this information. Whatever we have to multiply in the correct multiply by the correction factor, the value obtained from the table, the value, if you listen to me carefully, if you obtain the value from the table and TO bigger than 0.25, you need to multiply the correction factor. This is the only case, value in the table. But now we calculate U. Based on what? Based on the actual value. So this is the actual U because it is obtained from the actual value. This one no need to multiply by correction factor. Either whether TO is smaller than or bigger than, it doesn't matter because this is the actual value of U. The value of U, which is a specific power that need to multiply by correction factor, the one you obtain from that table. I'm highlighting this one, please be careful. The one you obtain from the table, and in case of TO bigger than 0.25, then in this case, you need to use a correction factor. This is the only case. Something else. Here is given the cutting speed and given the cutting force. Sometimes don't directly give you cutting speed and cutting force. I may give you not cutting speed and cutting force. I may give you shear stress and cutting speed. Listen to me carefully. Shear stress and the cutting speed. Then to get the power, you need to multiply FCV. We don't have FC. How to obtain FC? He give you shear stress. If he give you shear stress, then you have to obtain shear force. You get the shear area and shear stress, then you get the shear force. And when you get the shear force, you can get the FC from the shear force, then you can obtain the power. Then this is also something you have to consider as well. I will not give you direct problem. I will not give you FC directly and V. Probably don't give you the cutting speed, give you the VS. If you have VS, you can use the speed triangle and then you get the cutting speed based on the speed relationship with the angle. He give you the angle and give you the shear velocity, then you can obtain the cutting speed or cutting velocity based on the cutting velocity triangle. Then all these kind of things you have to consider and keep in mind while dealing with the problem. At the end of the chapter, there are some solved problem, really nice solved problem. We are going to show together and discuss, and it highlighting all whatever I'm discussing about. Right. Yes, I'm listening. Any question? Ahmed, you need to ask, right? Any question?
No, doctor. Sorry, I just clicked raise hand by mistake.
A mistake. Okay, so no question in generally. Anybody would like to anybody would like to ask? Okay, perfect. If no question, meaning okay, clear, then move forward. We have a different we call gross power. Gross power, guys, means the machine power. The word gross power, the word gross power, it means that machine power. All time remember, gross power meaning machine power. Machine usually have some efficiency. Listen to me carefully. There are a power needed in the cutting, and there are a machine power. There are a power needed in the cutting. If I told you this is a machine, this is a machine, right? Let me write. This is a machine. This is a machine. So this is a machine to be used in the cutting. Sorry, let me do in different way. This is a machine. This is a machine to be used in the cutting. This is a spindle, for example, and this is a tool, right? This is, let me write here, machine. Machine, right? This is a machine. Okay. And this is a tool. And this tool, there are a cutting here. This is a cutting. At the tool, there are a workpiece. Let me say there are a workpiece here. And then the power needed in the cutting. Cutting will happen here. Cutting will happen here. There are a motor. There are a machine. What is the machine power to make the cutting? What is the machine power to do the cutting? The power needed, the power needed to do the cutting. Power needed to do the cutting. The B is the machine power. And both are different. BG is the machine power. And BC is the power needed for the cutting. This is the power needed to do the cutting process. And this is the BG is the gross power or machine power. The machine power. Definitely machine power must be bigger than the power needed in the cutting. For example, if you need to cut this material, need power to cut this material 1 kilowatt, then machine power must be bigger than 1 kilowatt. Why? Because there are a machine efficiency. Machine efficiency, we call it, is a machine efficiency. If the machine efficiency 1.5, if the power is machine power 1.5, and the machine efficiency definitely less than 190%, then what is the power that you can just get from the machine? Definitely less than 1.5. Then the machine power equal to BC divided by efficiency, machine efficiency. So usually machine efficiency less than 1, and then machine power must be bigger than the power needed to do the cutting process. Okay, let me just give you an example. In a turning operation, on stainless steel with a hardness to Brennan hardness number, the cutting speed is 200. This is a cutting speed, right? 200. Feed is 0.25 millimeter per revolution. Depth of cut is 7.5 millimeter. Okay, VFD. This is a material removal rate can be obtained, right? VFD. How much power in the lathe drawn in the performing the operation machine efficiency 9%, and use this one to obtain the unit power. Unit power here can be obtained from the table in cutting stainless steel. In cutting stainless steel, unit power is this one. This is the unit power, and we have VFD, then material removal rate can be calculated. This is a VFD, this is a material removal rate. So material removal rate multiplied by the unit power, you can obtain the power. Then power can be obtained as 17.5 kilowatts. 17.5 kilowatt is the power to do the cutting operation. This is the power needed to do the cutting operation. However, we're going to use a machine with the efficiency 90%. So what is the machine power? Machine power equal to is 17.5 divided by 90%. This is a 17.5 kilowatt. This is what we need to have. This is what we need to have to cut the workpiece. 17.5 kilowatt. This is the cutting power. Machine power must be bigger than power equal to the cutting power divided by the machine efficiency. Then it's 19.44 kilowatt. Then machine power 19.44 kilowatt. If the machine efficiency, if the machine efficiency 100%, then the output power is 19.44. But it is not 100%. Machine power only 90%. If machine power 90%, then output is 17.5 kilowatt. Then the minimum machine power required to cut 17.5 is 19.44 kilowatt. Any question? This is the gross power or the calculating the machine power considering the machine efficiency. Any question? Okay, that's it. So next we're going to talk about the temperature in the cutting. Temperature in the cutting. Actually, as you know, in the cutting temperature increase. As you know, in the cutting temperature increase. Why? Why temperature increase? This is a tool actually. This is a tool. This is a workpiece. And this is a chip. This is a chip. This is a tool. This is a workpiece, right? As you can see here, temperature increase. This is a temperature gradient actually. 600, 650, 700. The maximum is here. Maximum is here 700 and so on. This is in the chip also gradient the chip and so on. Temperature increase. Why? Why temperature increase? Actually, because many reasons actually, because we're shearing the material. Temperature increase because we're shearing the material, and then when we're shearing the material here, this mechanical energy lost will become heat, and also friction here. We have high friction here, friction between a chip and tool here, leading to also temperature increase in the cutting zones in high temperature here and in the shear also. So shearing a material and also friction in the cutting zone increasing the temperature. Okay. Primary shear zone here increase the material will increase the heat, it will increase or temperature increase in the primary shear zone and also in the secondary shear zone because of shearing, here because of the friction, and also will increase here in this area, in the contact area between the tool and workpiece because of the wrapping because the tool here wrapping the surface also, so temperature increase in three area, here, here, and here, right? Heat cause temperature rise, and this one leading to many problem. What is a problem? First, actually, many problem like tool become soft, the tool hard, but when temperature increase, the tool become more soft. It will become softer, not rigid enough to cut. If tool is affected by the temperature, then become not rigid enough to do the cutting process. Damage in the machining surface also, uneven temperature cause distortion in the workpiece and cause dimensional change in the workpiece and so on, and more severe effect if the temperature here increase significantly. Some elemental migration happen between tool and the chip. The hard particle from the tool go to the chip, and the soft particle from chip go to the tool. Tool become more softer, and then this one will damage the tool also as well. Then we have to control the cutting speed. We have to not allow temperature to increase up to certain limit. We have to control the temperature. We don't have to allow temperature to increase up to critical limit. If temperature increase up to critical limit, many problem will be associated with the cutting. So we have to reduce the temperature actually. So okay, temperature pattern. This is a temperature pattern as you can see here in the cutting. It mainly related to the cutting speed, depth of cut, feed rate. I mean cutting condition. Whenever you change the cutting condition, then temperature increase. So cutting speed, feed, and depth of cut. Change cutting speed, higher cutting speed and depth of cut and feed rate definitely will lead to higher temperature. Cutting fluid being used here can reduce it. So can control by the cutting fluid. So also thermal conductivity. If the workpiece material have a good thermal conductivity. This one can dissipating heat quickly, but if bad thermal conductivity, then this one having the inverse effect on the temperature, and then temperature rise in the cutting zone. So it depends on this kind of condition. Most energy will be dissipated by a chip. Chip is releasing the highest amount of energy, and workpiece is next, and tool finally is the lowest part can dissipate the energy or heat in the cutting. This why we have to go through calculating. We need to know whether what is the cutting temperature. We need to know what is the cutting temperature. We have to know actually. As I told you, this is not good to allow temperature to increase up to critical limit, because this one affecting the cutting generally. We need to control the cutting temperature. We don't have to allow temperature to increase, right? First, we need to know how to reduce the temperature. If temperature is going to increase, how to reduce? By cutting fluid. However, using cutting fluid, not always good. However, using cutting fluid, not always good. Why? Because cutting fluid increasing the cost. Whenever you use cutting fluid, the higher cost you have to have. I mean, this is one you have to pay more money, and this one also leading to the price of the product in the market will be higher. Not only that, but also using cutting fluid also is another problem with the environment, because this one we have a many issue, we have a many problem for for recycling. There are no recycling, disposing, I mean, this cutting fluid, because it is harmful for the environment and healthy, also affecting people working with this one. I mean, in conclusion, using cutting fluid not always good. We always use the cutting fluid whenever we have to do it and we have no choice. Then we have to calculate actually the cutting speed, the cutting temperature. We can see that if the cutting temperature really high, then probably we can decide to use the cutting fluid. But if the cutting temperature is not that high, then we can decide to not using cutting fluid. Actually, it's better if we're not using cutting fluid. You keep that in mind. Then Nassim Cook is a scholar who proposed this kind of empirical equation to calculate the temperature rise in a cutting zone. This one equal to 0.4 U divided by rho C multiplied by VTO divided by K power 0.333. Okay, U is a specific energy, rho is a density, C is a specific heat, V is the cutting speed, T1 cut chip thickness, K is whatever we call thermal diffusivity. And this thermal diffusivity equal to K divided by rho C. K is the thermal conductivity divided by rho, which is a density multiplied by a specific heat. Okay, delta T is the temperature rise, U specific energy, cutting speed, Q1 cut chip thickness, rho C together. Rho is the density, C is the specific heat, but rho C together as one, we call it as volumetric specific heat. Volumetric specific heat. We call it like this. Volumetric specific heat. Rho C is a volumetric specific. Rho is a density, C is a specific heat, but rho C is a volumetric specific heat. K is a thermal diffusivity, and this thermal diffusivity equal to K divided by rho C. This equation is good equation actually to predict the cutting temperature or the temperature in the cutting zone, and we using this one is really very useful. This as an example for the specific energy obtained, like this is a specific energy, this is the U given, this is the U given, calculate the increase in temperature, which is delta T is the increase above the ambient, which is a 20 degree. Use given data from the previous example. V equal to 100 is given, TO is given. In addition, the specific heat of the material is given, which is a C. Volumetric specific heat, which is the rho C is given. Thermal diffusivity is K is given. then must be know that calculate must be convert the speed here. This is the unit. We change here the unit to make it millimeter per second because all unit in millimeter. Speed here is multiplied by 1000 divided by 6 to make it millimeter per second. To make all unit in equation is same, and then you can apply point for u is given, v is given, tu is given, rho c given, k is given. You apply, then you can obtain the temperature. This is the delta T actually above the ambient. This is above the ambient. Above the ambient mean if you would like to calculate temperature, you must add it 20, which is ambient, then you get the temperature in the cutting zone. When you get the temperature in the cutting zone, then you can realize that whether this temperature is okay or not. Did we exceed did we reach the critical temperature in the cutting zone? You can know whether okay or not. If no, then should be fine. We can use the dry cutting. But if really temperature exceeds the critical limit, in this case, probably cutting fluid should be considered. This is the importance of using this equation actually. Another guy, he call it is the Kent trigger. Kent trigger propose another equation to equal to kvm, and the k is constant and v is a speed, m is another constant. K and m are constant depend on the cutting condition in a work material. So yes, I'm listening. Okay, this kind of Kent trigger equation can be obtained. This K and M value can be obtained. Actually, this is not very common, but it's another. It is not accurate as the one we showed previously, but this one also being used, but not really is not very accurate as the previous one usually. So I will stop here, and will next time we'll discuss about solved problem about this chapter. I will stop recording.